In this video, we're now going to return to the challenge of working with formulas and antiderivatives or integrals. We're going to start with what is considered the most straightforward method, the method of guessing and checking. The idea is that we can take an educated guess sometimes at what the integral would look like and then tweak it, hopefully with some constants or some relatively easy manipulations, to get to something that matches exactly what we need. This is much more easily seen through a few examples. So taking what you know already about derivatives, imagine trying to compute the integral of cos 3x dx, or asking yourself, what would I have to differentiate? That's really what the antiderivative question is, to get something that looks like cos of 3x. Take a moment to look at the options here, and then we'll check in. All right. Right off the bat, if we're going to have a 3x inside the function, we have to have a 3x in the inside of whatever we're going to start with. We can't have just x, because that will never increase the coefficient inside the function. The chain rule, the derivative rules just don't work that way. So that rules out the first two options. And then we might think, well, what do I differentiate to get cos? I might differentiate sine. However, this is not actually equal yet. If I differentiate sine of 3x, I get cos of 3x times 3. So we're not quite right. This is a good guess, but it needs correction, or needs tweaking. And fortunately, it's not too complicated to do that. If we're going to say the integral of cos of 3x is something like sine of 3x, and including our constant, that doesn't hurt, the way we can check this is working our way backwards. I like writing it underneath as saying we've got sine of 3x plus c, and then saying what's the derivative of that. So we're working this way on this side, and left to right on top. If we differentiate the sine of 3x plus c, we're going to get a cos of 3x times 3 plus 0. Then you just compare these two answers and go, well, I'm close, but I have a 3 I do not want. Well, how can I get rid of that 3? I can divide through by 3. Well, I can't just do it here. I would have to have divided this entire thing here by 3. No, but if I do that, then we're done. We would have cos of x, cos of 3x rather. And that is perfect. Cos of 3x is what I should get back when I differentiate this. And so we just translate that up here, recognize I would need to have a 1/3 sine of 3x plus c as my integral function, as my antiderivative function. And the check is, if we take that, run it through our well-understood derivative formula calculations, we get back to cos 3x, and it's that cycle. The integral of cos 3x is this, because the derivative of this is cos of 3x. Let's try that on another example. We want to integrate e to the 7x minus 2 with respect to x, and our first guess is that it would look something like e to the 7x minus 2, maybe plus a constant. We should include that for any general indefinite integral. Well, let's find out if that makes sense. The only way we can really check is by differentiating. We'll take the derivative of what we have here with the c, and we're going to go backwards, just for physical alignment here. The derivative of e to the 7x minus 2 is going to be e to the 7x minus 2 times 7. We take the derivative of that exponent. Well, I don't want the 7. I'm trying to match this function exactly, so we're going to add something ourselves. The way I get that dividing by 7 is by putting it in here as well, and that's going to work perfectly. If we have 1/7 of this and we differentiate it, the 7's will cancel, and we would get back to our 7x minus 2. And this are the same, therefore we have the right answer. So copying this as our full antiderivative now, the antiderivative, the integral of e to the 7x minus 2 is e to the 7x minus 2 times a seventh plus some constant. And that is the full guessing and checking method. Take a stab at the form of the integral, then check it and see, in particular, are there any constants that need to be sorted out before we can get a perfect match to the original function. Now what's interesting about those earlier examples is that they only had linear functions on the inside. Just going back quickly, we had a 7x minus 2, we had a 3x. In other words, they were just x to the power 1 involved. Take a look at this more complicated example, this integral of x e to the negative x squared. Now this is not as obvious, but let's take a stab. My guess is we're going to see something like e to the negative x squared back, possibly plus a constant. How do we know if that's right or not? We check. We're going to take the derivative, I'll leave a little more space here, of e to the negative x squared plus c. So we're going to differentiate this and work our way back. The derivative of the exponential is e to the negative x squared, but times the derivative of the inside, which would be negative 2x's. And we see, that's actually pretty close to what we want. We have an x, we have an x, we have the exponential, we have the exponential. The only thing extra that popped out was a negative 2. So let's just divide this term by negative 2, or do negative 1/2 of that. And sure enough, when we cancel the negative 2's, we get x e to the negative x squared. In other words, a perfect match to the function we started with. That means if we integrate x e to the negative x squared, we actually get something a little bit simpler, just the exponential by itself with a little coefficient out front. And we know that's correct because when we differentiate this, we get exactly back to the function that we started with. Now it turns out that it's crucial that we have this x here. What would have happened if there hadn't been an x here, if we'd just been asked to integrate e to the negative x squared? Well, our guess might have still been e to the negative x squared plus a constant, but when we went to check it, if we took the derivative of e to the negative x squared plus c, we would not have liked our answer anymore, because it would have given us, going back this way, negative 2x e to the negative x squared. Why is that so bad? Well, this time we would have a negative 2 and an x that we did not want. So imagine trying to do this. So let's just divide by negative 2x. That wouldn't have worked, because by adding an x to this little divising trick, negative 2 is fine because derivatives aren't affected by constants. But if we bring in an x here, we just blew up our derivative. If we were going to do this derivative, all of a sudden we would need the quotient rule. And we've just gone down a rabbit hole of ugly differential calculus now. In other words, if we had this function here, let's go back. In other words, when we have an x e to the negative x squared, things work out nicely because this x out front matches with the e to the negative x squared and the chain rule effect that causes. If we're missing that x, it's going to make life really, really miserable. In fact, fun fact, this exponential doesn't even have an antiderivative. You can look as long as you like, you're never going to be able to find a simple function that's its antiderivative. Doesn't exist. Wish it did. It's a very fun function. It's the bell curve, but it does not have a closed form antiderivative. And it's because whatever we try to make the antiderivative built out of, it's going to need to have some cancellations. It's going to lead to more complicated derivatives when we do our check of the final answer. On the plus side, this gives us an idea about how we might be able to handle some kinds of integrals, some forms of integrals, where we have an inside function and a result of the chain rule also lying around in our function as well, and that we're trying to integrate. We're going to formalize this in some upcoming videos on the method of substitution.